to the organizers for inviting me here. What I will present today is where it lies at the intersection between quantum information theory and quantum n-body theory. So it's based on joint work together with Mattias Christandel, and Spiros Soteriadis, and I also like to thank just Swiss Map in general, and because this work originates from a meeting with Mattias Christandel, who I met here at the research station 2 years ago. So without this place, this work wouldn't have existed. Also want to thank, actually, Didina was one of the organizers of the work, so I also thank her. So this is the result of discussions that started meeting Mattias here 2 years ago. Okay, so the basic problem I will discuss is this. So for any quantum information processing device, you want to be able to transfer information. So imagine you have, the basic problem is then you have two registers, register 1 and 2, or Alice and Bob, and you have information in one and you want to transfer it from that place to the other through some channel. So that's the basic problem. So it was proposed in a paper from 2003 that, well, there are many ways you can transfer information, but one way that was proposed in this paper was to, instead of transferring it using photons or something else, just transfer it with a spin chain. So you have the same system acts as both registers and channel. So that was the proposal in this paper, where, they asked the question, okay, can you do that? And by which fidelity can you do it? So in general, this has a possibility to lead to better transfer of information. And it was then realized shortly thereafter, or almost at the same time, that it's actually possible to have perfect transfer of information. So that's in this paper written by Mattias and collaborators, where, well, you're able to have perfect transfer, or perfect state transfer, they call it, in a spin chain. Think of XX spin chain, that's what they explored in this paper. If you can modulate, or if you're allowed to engineer the couplings between neighboring lattice sites. So the key is, of course, to you have a spin chain and you change the couplings between neighboring sites, but you do not want to allow for modulation in time. So that's a basic problem. Can you do this, which they showed, if these are static? And that's possible. In the case they found here is that if these couplings vary in certain ways in space. So the one that they found in the paper from 2004 was that these couplings, J has to be proportional to basically n minus j. So you get the kind of a square root type strength of the couplings. And then it works. And there are other cases where it works.
It works what?
That you have, imagine you have a state at time equals 0 that looks like this. And at time equal to 0, and at time equal to some capital T, you're able to produce the state where this one is pointing up and everything else is pointing down. So essentially, it will work for other states as well, but this state, you want this state to be effectively copied from that. You want to be that the time evolution on the dynamics with these coupling constants is effectively a reflection. So in that sense, if you had a spin up at this side, it's going to be spin up here, and everything else will be down.
But also if it's pointing in other directions. So
well, yeah, I mean, it's
general point of the
you want
block
to have the
state.
exact state. So on the Hilbert space, effectively.
Yeah.
On the Hilbert space, your propagation should be equal to a reflection at specific times, capital T.
So the many-body unitary is the reflection operation.
Yeah, exactly, yes, at time, capital T. Okay, so that has been studied a lot for discrete systems. And in this case, it relies on the many-body properties of the theories. However, it has not been explored in a continuous setting, which is what we set out to do in our paper. So let me define then, we introduced then the concept of perfect wave transfer to, is the same thing as what I studied before, but pictorially, what I have in mind is that, okay, you have some initial wave at time equal to 0, say center to the left, or place to the left, and you want it to be at some capital T. You want to find a Hamiltonian such that it's essentially reflected. So it's the same problem. And if you think of it as expectation values of operators, then you kind of have that, okay, if it's supported, if it looks like a wave initially, it should be like the same wave, but reflected on the other side. So to define it concretely, we'll say that a system will have this perfect wave transfer property if there exists some time capital T is such that any initial expectation value is equal to its reflection at capital T. And it should be true for all observables and all expectation values. So this is, in a sense, the strictest thing you can require. You can also think of ways to relax this. For instance, now it's for any expectation values, so to say for any state. But you can also look at properties where it would be holds for specific states of some interesting class. Or perhaps you can ask the question, if it is not possible to have perfect wave transfer, can you have almost perfect wave transfer, so up to some epsilon? So there are many questions you can ask. We, in our paper, now started with studying the perfect case, which is kind of, we wanted to sort that out first. Okay, so the outline of my talk. I will first discuss a bit, or mention a necessary condition for this to hold. And also then part of that is to reformulate the problem in different ways, which can be useful for different things you want to ask. And the first example I will discuss is effectively the continuum limit of this inhomogeneous spin chains that we studied before. And after that, we will discuss to try to answer what are necessary and sufficient conditions. We'll study a particular class of quantum n-body systems that describe, well, it's a prototypical example describing the low energy physics of a large number of systems. But in particular, we will let it be inhomogeneous in a sense that it will break conformal invariance. So we can explore properties with or without conformal symmetry. And it will actually, in the end, to solve that, I will review basically the solution using Sturm-Liouville operators. And we will show that to answer this question of perfect wave transfer, it boils down to an inverse spectral problem that we solved for this class, but you can imagine studying other models when you will find a similar inverse spectral problem, or you will find an inverse spectral problem that you would then have to solve. Okay, so that's a task. So first, one necessary condition. So just to establish some notation, we have a Hamiltonian H on some Hilbert space F. And let's introduce the parity operator, since, well, as I mentioned, perfect wave transfer now, I define it with respect to a reflection, so parity operator is, well, a little feature. And we also have the time evolution operator. So with these two objects, P and the time evolution operator, the definition I gave, that the expectation value of some operator at time equals 0 should be its reflection, can be phrased in this way. So the operator on the left-hand side, expectation value with respect to any expectation value, and any operator O, should be equal to, well, the same thing when you act with the parity operator and you evolve it in time. So from here, already you can convince yourself that what we're actually interested in is to show that the evolution is equal to the parity operator up to some phase for specific times t. And it can be many times t, but it should be a common time t for all operators and all expectation values, so for all states. T is fixed for the whole system. Okay. You can also phrase it like this: that for any, showing that this thing is basically the identity up to a phase is the same as evaluating it with respect to any state. It's equal to its initial expectation value. So this is the last one. Is useful to just establish the following result. So, and prove it now based on supposing that H has a pure point spectrum, which it will have in the examples I will give. Okay. So suppose H has a pure point spectrum, then reflection symmetry would be a necessary condition. So basically, the Hamiltonian has to commute with P. And to just briefly sketch the proof, one way to show it is that, well, this property should hold for any state phi. So in particular, it has to hold for energy eigenstates. And if you use that it must hold for energy eigenstates, if you try to study, say, this object, f of t, for any small t, then you can show that if it would not be an energy, if it would not hold for all energy eigenstates, this thing would never be able to be equal to 1. I mean, if this thing here, if that's the reflection, this one has a parity operator, right? So if this object, energy eigenstates, when it evolves in time, would just get a phase. And if this would not be an energy eigenstate of P, if there would not be an eigenstate of P, then you would have some linear combination, and then projecting with another eigenstate, it would be for sure less than 1. So this would not be possible to hold. Okay. So the system has to be reflection symmetric. Okay. So first of all, let's study the case which is basically the continuum limit of these inhomogeneous spin chains. I will assume these spin chains are in the gapless regime. So, and assuming also the spin chains have couplings that vary slowly in space. Okay, so smoothly. Yeah. So one can show that the corresponding Hamiltonian in the low energy limit would be exactly that of an inhomogeneous CFT. So I'm basically trying to define what I mean by inhomogeneous CFT. It is the same as a standard CFT, but you allow the velocity to vary in space. So this T plus and T minus, that's the components of the stress energy tensor. They satisfy, if you fully transform them, they satisfy the relations of the Virasoro algebra. So if you have the content of a CFT, usually this V of x would be a constant. Now it's varying in space. That's directly related to that the coupling constants would vary the coupling between neighboring sites in the spin chain would vary in space. Okay. And we'll assume it's smooth, so things are easy. And since we're interested in transport from one side to the other, it's important to impose realistic boundary conditions. So the boundary conditions are important. So the case that is, meaningful here is to have Neumann boundary conditions. So no waves propagate out of the system. When you hit the boundary, it gets reflected. Okay. As a specific example, we can take inhomogeneous free fermions, which is exactly the case corresponding to the spin chain studied by Matthias and collaborators in 2004, the corresponding continuum. So in this case, you have right-moving and left-moving fermions on a line with Neumann boundary conditions. Okay, and in this way, you can actually identify what is T plus and T minus in this case. Okay, so you can try to plot what happens. So, for any state, but let's take a specific class of states. Think of one particle state. So you're basically creating, you have your vacuum and you act by psi plus dagger and psi minus dagger on this vacuum. That would be our state. So what I'm plotting here is for the free fermion case, you have an initial, basically a delta-like peak at time equal to 0. So what I'm plotting here is the intensity plot when you have that state, and you compute basically the overlap with a state that is probing the entire space. So the first state is localized at this point, and psi is all points in space here. And you can check that, what happens is that for time equals 0, things are localized here, and then it will split into two waves, one moving to the left, one to the right. The left one hits the wall and reflected back, and they are propagating not on straight light cones, but on light cones that are varying in space, and they're varying according to the velocity profile that we picked. So that's one example. We work for many other profiles. And at the end, they recombine to this point here, which is the exact reflection of this point. And this will work then for any other, if this is a delta-like, if you can study other ways by just adding up these contributions. So in this case, it's not surprisingly, it works.
Sorry, can I just check? It doesn't seem terribly surprising that you can arrange it to work for some specific starting point for the wave packet, but you might imagine, for instance, that the choice of the time capital T would have to be different for different starting points. So you're saying that...
I want it to be the same for all.
And it's possible to
Yes.
fix that.
Yes, that in this case it's possible. So the question I want to ask is exactly, that's the property we're wanting to explore. And you can think about cases where you can relax that property, but I think of it in a stricter sense, it should be the same for all initial waves at the same time. Yes?
I'm guessing that, at least just going back to the lattice, the reflection many-body unitary is not a low-depth unitary.
Sorry?
Is not a low-depth unitary, which is to say that if you were to try and compile it into a series of two-side gates, you'd have to make it extensively deep in system size. And is it correct to say that that's what's being reflected in the fact that the couplings in your Hamiltonian basically have to scale with system size?
No, they should, what is, they should only be proportional to this. This is how they should vary. I didn't say what the overall strength of...
what is J times capital T? Does it
J
grow like
times
N
capital...
at its maximum? Or?
J is just the labeling of sites.
No,
Oh, no.
capital J. I mean...
Capital J. Okay. So what's important here is now you can add any factor in front of. It was the base. The important thing.
J times T. That's, I guess that's what I'm asking.
Capital J times T.
Times capital T.
How
is that scaling?
yeah. Okay. So there is a relation between. We'll see it for. So what I will explore is not for the lattice, but you will see that. I mean, of course, you can relate the capital T to. So now I can only explain it for you for in a continuum, but this capital T will depend on the strength of your couplings. So what we will see later is that this T will be proportional, or it actually will be equal to L divided by V naught, where V naught is the effective time to travel from one side of the system to the other.
I guess maybe I can say my question more simply, which is if you just look at H times capital T, it'll be a sum of, like fermion bilinears or whatever. The coupling constant in that, what's its maximum value? Is it increasing with system size, or is it just order 1? I suspect it has to be increasing with system size because this reflection operator is like a non-local unitary, right?
Can we get back to the question later on? And maybe it will be answered, since phrased in terms of lattice, I don't have it in my head.
Okay,
but in terms of the continuum system, then we will see exactly how things are related to each other. And of course, going from the lattice to the continuum, there's some non-trivial scaling involved. So, yes?
Yeah, sorry, I had a very basic confusion. So you want to transfer information from one product system to another?
Yes.
Why are you even deforming the? Why can't you just have free propagation?
Yes. So, of course, for this example, I didn't have to deform. It was crucial on the lattice. On the lattice, just having the same couplings between neighboring sites, it will not work. So that you can show. So on the lattice, it doesn't work. It turns out that in the low energy limit, it works independent of the profile V of x. It only has to be even, since we already established that it should be reflection symmetric. Okay, so that's one clear difference between the lattice and on the continuum. On the lattice, this case when there was this kind of square root, this profile was special. It's not the only one.
Just to understand, in the continuum, you would be happy with V constant.
In the continuum, it would be happy with V constant. Yes, for this model, I mean free fermions, right? Or any CFT. I mean, at least for any CFT, you would expect it to work because in CFT things move ballistically. Although, I mean, to prove that, you would have to do these computations for all kinds of states, many body states also, many particle states. So that's quite an involved computation. But for one particle states, this works for any V of x, as long as it's even. So that's a clear difference between lattice and the continuum.
What does one particle state mean?
Here I just kind of created one excitation, one fermion on the vacuum. But if you want to compute, so essentially this boils down to a two-point function, right? This one has creation of psi dagger, this one has psi. So it's a psi dagger correlation function. If you have more particles, to these ones acting, I mean, another one as some other point, y, then you will have a 4-point function, and so you have to compute those. Okay, but I mean, since in CFT things move holistically, you kind of expect that it should work out, but I mean, you have to do the computation to show that, and it's quite, maybe you find some general arguments showing it's naturally true, but as far as I see, one has to do some non-trivial computation to show it. Okay, so there are differences between the lattice and the continuum. So what I mentioned now is that, okay, for these free fermions, this V of x didn't actually have to be there. It's not a constant. Okay, but the question is then, what are necessary and sufficient conditions for perfect wave transfer and for general excitation? So not just creating one particle excitation, I mean for all excitations. Okay, so to do that, we'll look at this class of so-called inhomogeneous to Monaga Luttinger liquids. The reason being that I do not want to assume conformal invariance. So I will look at a model where I can break conformal invariance in a controlled manner. So I can play around with having both conformal invariance or not having it. Okay? And so I do that for this class of models. And we want to study what are necessary and sufficient conditions for perfect wave transfer to hold in this case. And of course, you can imagine looking at other models, and that's part of a bigger program. We want to study, or so far we studied this case to try to understand the properties of the system. Okay, and the properties of when perfect wave transfer is possible or not. Okay, so let me define the model. So now it's phrased in terms of a bosonic field, phi, and its conjugate, pi. And you have two quantities that depend on position. Two things we generalize to being dependent on position. The velocity v of x, as in CFT, or in the inhomogeneous CFT, but also the so-called Luttinger parameter is now made position dependent. And this one can show will break conformal invariance. Okay. This example of inhomogeneous to Monaga liquids has, how you say, it's an important low energy description for a large number of systems. One being spin chains with varying couplings, more general spin chains than just the XX case studied before, but also XXZ with the anisotropy being position dependent, independent of the overall couplings. Then you will get a non-trivial K of X. And in cold atoms in traps. So these systems are intrinsically continuous, so that's kind of one of the motivations for studying perfect wave transfer in a continuous quantum system. And in this cold atoms in a trap, the trap explicitly breaks translation invariance, and if you derive the low energy theory, it is unique to have both a V of X and a K of X. So that's another very important example. Okay, and just to highlight this, if K is constant, then it is a inhomogeneous CFT. It's only V of X there, and there will be an example of a CFT. And if K is equal to 1, it's exactly the bosonized version of the free Fermi case that I showed before. Okay, so first just highlight the importance of K of X. So if K of X is non-constant, the derivative is non-zero, and it effectively couples right and left movers. So to say, you can no longer split into right and left movers globally in the system. What is right and left at one point in one point in space is not the same as another point. So you have basically an effective backscattering between in a system. Okay, and let's also impose open boundary conditions. So we want the current at the left and right hand sides to be zero at the edges. So that's if phrased in terms of the field phi, then this current operator, this V of X times K of X times dx phi, should be zero at the boundaries. And we will, in the regular case, assume that V of X and K of S are positive. So this is Neumann boundary conditions. Okay? But you can try to generalize to other cases where, say, V of X goes to zero at the boundary and so on. And these are also important examples. And one more assumption, just to simplify life, that is, at the boundary, we assume that k prime of x is 0, just so that, I mean, since at the boundary, you're already coupling right and left movers through the boundary conditions, and to make life simpler there, let's assume they're not coupled through k of x. Okay, otherwise it gets a bit messier, everything. Okay, so I want to study this model, and I want to study, yes?
The making of a conformal comes from the fact that k prime is non-zero.
Yes, yes. One way to see it is that, I mean, in a conformal field theory, you should be able to split into right and left movers everywhere. You should be able to define t plus and t minus, the light cone components of the stress energy transfer, and you cannot do that here. It will not, yeah, it will not separate in that way. Right and left movers will talk in this case.
Yeah, or maybe you can still write the theory.
Sorry? Maybe we have to define some other, but it will not be the same as in CFD. I mean, you will not find the Virasoro algebra. Yes. And of course, there are many ways to break conformal invariance. I picked one. Okay. Yes?
Sorry, you might have mentioned this already, but can you once explain the origin of k of x? Like.
Okay. So now there are many ways to think about it. You can take the perspective that you have some original theory and you want to derive the low energy description of that. Then k of x will be related to some property of your initial, of your original many-body system. So that is a perspective when you think of this as an effective field theory for, say, ultra-cold atoms.
Ultra-cold atoms in a trap or?
In a trap, yes, you need to have the trap.
So the trap is causing this k of x?
Yes. So in a sense, with the trap, you will have, if you compute the average density profile with the trap, is proportional to the, related to the trap, and this average profile, density profile, determines both v of x and k of x. Okay. So that's for that case. But there are many other cases when you will have this. And in general, if nothing else, you can think of it as the most general case you can look at for compactified free bosons. I mean, this is a sum of two terms, and I can have some coefficient capital A of x times this term and capital B of x times the x phi term, and I just parameterized A and B as one is V over K, the other one is V times K. So it's the most general one of the compactified free bosons we can look at. Okay. So that has close connections to what's been studied in high energy theory. But I will not go into those. If you're interested, I can say something about it at the end. Okay. Well, one short comment I can give is that it's related to this k of x is essentially a non-exactly marginal deformation of your original theory of your basic compactified free bosonic theory. But I mean there was many things said in one sentence that's perhaps not so illuminating. Okay, so let's now try to solve this system and try to study when we can have perfect wave transfer. Okay, so to do that, I will use Sturm-Liouville theory. The basic observation being that, well, you have your Hamiltonian, HITLL, and by doing a partial integration using the boundary conditions, you can identify an operator A that acts on this field phi that is exactly of the form of a Sturm-Liouville operator. So if you're familiar with some courses you had on ODEs, then this is one very important class of ODEs that has been studied a lot. So the general form of these Sturm-Liouville operators, you have a weight function, W, so it looks like 1 over W, and then you have some coefficient P of x in between its derivatives, and you have a Q of x. It looks kind of like a mass, or is it external potential. In our case, we can identify what W and P is in terms of K and V. And since these are massless, Q of x is 0. So we have no external potential. We have looked at the case when you allow for a mass term, and then you will get a non-zero Q of x. So that's also in the paper, but I'll leave that for those who are interested to take a look in the paper. Okay, so you have this operator, and this is an operator that acts on a space of smooth functions. And this domain of functions should be such that, well, dx of u is 0 at the boundary. So you have normal boundary conditions. So this is the class of functions, and this is operator axon. And having identified that we actually have an SL operator, we can use properties of that SL operator to solve, or to basically diagonalize our Hamiltonian. So the way to do that is that, well, we want to study the eigenvalue problem for the SL operator. And it's important to distinguish between regular and irregular stimuli problems. That's important because for regular ones, a lot of things are guaranteed. And for irregular ones, they are not guaranteed, these properties. They might still hold, but nothing promises. You have to look at case-by-case basis. So let's assume now that our problem is regular. And if it's regular, this eigenvalue problem, a u equal to lambda u, has the following properties. So one, the spectrum has just eigenvalues, and they are ordered, starting from, well, it could be 0, but larger or equal to 0, and then they must be strictly ordered. And each eigenvalue has a unique eigenfunction with isolated zeros corresponding to the label n. So, and they form a complete basis. So with the weight function w. So these three properties are guaranteed. And another thing that one can show, and that is more like a global property, which follows from Weil's law, which is a general theorem for well, Laplace type operators. And that is, you can show that this lambda n can at most grow as n squared for large n. So that's also constrains the system. And we'll get back to that towards the end. Okay, so just briefly Weil's law. It's stated for SL operators. It gives you an asymptotic relation for the ratio between the number of eigenvalues at some lambda, or to the left of some lambda, and square root of lambda. So this ratio has to satisfy this relation for large lambdas. So it depends only on the square root of w of x over p of x. And in our case, given what p, we know what w and p is in terms of the Luttinger parameter and the velocity. So this is just the velocity. So, and the number of eigenvalues, well, we know how many eigenvalues there are lower than some lambda n. They are proportional to n. So n over square root lambda n must be some constant if this integral converges. And this integral is essentially the average time to go from one side of the system to the other. Okay, so this is actually going to set our time scale for our problem. And so this statement is this, that if this converges, then lambda n, square root lambda n can as most goes as linear in n for large n.
I'm
Yes?
slightly lost track of what you're trying to do. So you're trying to come up with an operator that affects a reflection on the system that's bounded and in a trap.
I want to see if that's possible to do, when that's possible.
Okay.
So what I'm trying to do now,
A W and a
Yeah.
P or
yes, so what I did now, I picked a specific class of models, and now instead of computing, say, overlaps of states, I'm studying the spectrum of it. And this actually, in a way, perfect weight transfer is relates to the spectrum of the problem. I mean, it should be a statement on the full Hilbert space. So if I can understand the properties of this Hilbert space, then I can understand whether or not I can have perfect weight transfer. So right now, I'm just trying to, so to say, well, it's a detailed thing, the details for studying this particular class of models, and I'm trying to effectively just diagonalize it and write it in terms of something we all are very familiar with. Is just well, quantum harmonic oscillators.
Well, what might have thought happened is if you look at this sort of putative Hamiltonian thing and then look at the Heisenberg equations of evolution for your fundamental fields under it and ask, can I choose a W and a P such that after a certain amount of time t, the Heisenberg equation of motion integrates up and says that 5x becomes 5 minus x.
This is
That's what you do.
we'll get at. Well, maybe phrased differently, but this is okay. So this is why. So one thing to keep in mind is that since it's a field theory, and I didn't impose any cutoff of momentum modes or this n, then this is an asymptotic relation that we will have. So this constrains the theory. Okay. So one thing I know now, and I have eigenfunctions u of n from my Sturm-Liouville operator, and I know that they are well, the full basis and all these nice things. Furthermore, since q of x is 0, you can actually show that the first one has to be constant, and so the first eigenvalue is 0. But the property saying that, well, I have a complete basis, or normal basis, allows me to expand my field phi of x and pi of x. So I expand them in un with some, well, operators u, phi n, and pi n. And if I do that, these operators u, phi n and pi n satisfy the usual commutation relations for bosons, and the Hamiltonian becomes, well, effectively a sum over harmonic oscillators, the quantum harmonic oscillators. So if you then can understand, well, if you're then familiar with, what we need to do is, well, if you know properties of harmonic oscillators, then this is just going to be a sum over an infinite number of those. Okay? However, n is no longer, it's not momentum, it's something else, right? It's just a label. Okay. Right. So here's the result. I maybe position it a bit like not so readable, but I also want to give you some hint at the proof on the same slide. So in order for this class of systems to satisfy perfect wave transfer, first of all, you can show that these eigenfunctions UN must have definite parity. So acting with the parity operator, then they must have a well-defined eigenvalue for those. But it's not strange, since we already know that system has to be reflection symmetric. Okay? And two, they must satisfy, the eigenvalues must satisfy this condition that En times some common t, the smallest common t actually, must be equal to pi times an integer. And the reason for that I will explain when I try to sketch the proof. Okay? And then there are some properties for these integers, mn. And the reason why this must be satisfied is that, well, take any operator, O of t, and evolve it in time. Okay? And these operators in our theory now, they are built from phi of x or pi of x. I mean, that's the operator algebra. So you can take O to be phi of x if you like. And if I decompose that into in my un of x and write it in terms of an, then this is the expression for the evolution of this, the time evolution of this operator. Now, for perfect wave transfer, I want this operator at time equal to 0 to be equal to its reflected version. So, and using linear independence, that means that each of these terms has to kind of match each other. Okay? So what happens is that, well, comparing this at time equal 0, you have un of x. At time equal capital T, it's un times minus x times e, well all this expression right hand side here. So this must have an equality here. So what you see here now is that, well, just rearranging a bit, you can see that this actually means that un of x is an eigen function of the parity operator, and that this phase here must be an eigenvalue. As if the eigenvalue is the parity operator plus or minus 1, then this phase here must be an integer plus or minus 1. So that means that this energies En must be integer, basically up to some factor pi. So, okay. So this is what shows that you must have an integer spectrum. Okay. So this is the first of all, I mean this obvious claim, but this just to explain things. This un of x have definite parity if v of x and k of x are even. Okay, that's rather easy to show. Okay, so now is the main result. An inhomogeneous to monoidal liquid shows perfect wave transfer if v of x and k of x are even, and all eigenvalues are of the form that they're integer up to the common factor pi of x. And these integers, since we know a lot about the Sturm-Liouville problem, it actually implies a lot of things for these integers. So we know that they must be ordered. You can even show that if you look at the n being odd or even, then the corresponding m must be odd or even. All these things, because this just follows directly from the Sturm-Liouville properties. What you also know is that these integers must scale as n for large labels n. So that's a quite strong condition. So this follows directly from Weil's law. Okay. So that was the statement, kind of. What we showed is when it's what's required. Now we can flip it around and say that, okay, if we are given a spectrum that's integer in the way that I I explain with these properties A and B, what possible Sturm-Liouville operators can realize that, or in a sense, given a spectrum, now you have an inverse problem, find the Hamiltonian such that V of x and effectively finding V of x and K of x such that that realizes that spectrum. So that's now what one study. So before doing that, let's just look at two examples. So example one is the case when the spectrum is exactly linear. So this Mn are exactly equal to n, right? That will happen when K of x is constant. Since if K of x is constant, your Sturm-Liouville operator looks like it does here. You have a common V of x times dx, V of x times dx. So now I can do a change of variables. I define some y that is basically an integral of 1 over V of x, up to some rescaling, so things are kind of defined on the circle in a nice way. And in this new coordinate, my Sturm-Liouville operator is just Laplacian. So if I can solve that with non-boundary conditions, I know how the system behaves. And well, those are very well known, right? It's just going to be cosine, and the eigenenergy is just going to be exactly linear to proportional to n. Okay, so this is the conformal case. K of x is constant. There's no backscattering or effective backscattering in the system. And this will enjoy perfect wave transfer. Another example is actually an irregular system. So now let's take V of x being this square root profile. It's the same square root profile as here, just that here I labeled it from lattice size from 0 to n, and this system is from minus L over 2 to L over 2, so just recentering what is the origin. Okay, so let's take this V of x and K of x being similar shape but with some power alpha. So that's an irregular Sturm-Liouville problem, but you can actually show that the properties that I mentioned still hold. So you have an eigenbasis that you can expand in and so on. And they're actually given by Gegenbauer components. And what you can show is that the eigenvalues now look like n times n plus 2 alpha. And what we want is that this square root of lambda n should be integer. So the only case when this works is when alpha is 0. So again, this case has K of x actually being a constant. Okay, but we can still plot and see what kind of happens. So for when alpha is 0 is this plot, then we plot the same kind of propagation as we did for free fermions. And what you see is that after you have some initial wave packet at time equal to 0, and it's exactly reflected at time equal capital T. So he's plotting the profile or the absolute value of the intensity at time equals 0 is the red one, and the black one is exactly a reflection of the red one. And for the other cases, you can clearly see that it's not a reflection. Okay, so that's not surprising. The question is, can you have something else than K of x being constant? So that's what we try to study. So we want to solve this inverse problem for Sturm-Liouville operators. And to do that, we can use known theorems when doing it, but that's based on first moving to what's called Liouville normal form. So we need to define new functions, your original eigenfunctions u of x times square root of kx, and you do the same change of variable, then you can define what is an effective potential, q hat, in this new variable y, and in this this is then given by the content of our original Sturm-Liouville operator, and with these changes, what happens is our eigenvalue problem becomes effectively the same as that of a Laplacian with an external potential. The external potential being q hat. Okay. In our case, q was 0, so this term is gone. So the external potential is given directly by k of x. Okay. And as we define things, the boundary conditions are unchanged. It's still going to be Neumann. So we want to study this eigenvalue problem. And actually, this is at some point I had kind of stopped exploring since, I kind of assumed that this has been studied, but I didn't know where. But it turned out that in a paper from 1946, this problem was studied in depth in this paper in Acta Mathematica, and well, I actually managed to get some use of my German skills, no matter how limited, to understand actually finding the theorem in there. But it's very well summarized in this paper by Norman Levinson, and it's the theorem 2 here, which relates to the case when their external potential is what is actually reflection symmetric. So that's exactly the case we have. Okay, so but these two papers solve the problem not in terms of reconstructing, but giving statements on uniqueness of the problem, at least. So you have the following theorem, or paraphrased. But if you have an even potential, q hat of y, then that uniquely this potential is uniquely determined by the spectrum if you have normal boundary conditions. So that's exactly what we need. In general, this will not be true. If you try to solve these general inverse problems, you actually need to have 2 copies of the spectrum for different boundary conditions. But in this reflection symmetric case, you only need 1. That's good, because we only have 1. Okay, so now we know that the spectrum uniquely defines q hat. So you can view q hat as given, and just rearranging this equation. Of course, q is 0 in our case. This is second order ODE for k of x. So, well, second order ODEs are also well studied, and it then follows that, well, assuming that this profile, this potential is continuous, what happens is that this one will uniquely define k of x up to a rescaling. So usually you will have, of course, two degrees of freedom when you solve ODE, but we also have, of course, evenness, which takes care of 1, so you only have an overall rescaling. Key thing, of course, being that, well, we need our solutions to be positive, so it's not highly guaranteed, but this is the problem. So that this uniquely solves our problem. So we know at least that if the spectrum uniquely determines the potential q hat, and from there we can say that k of x should also be unique. So we have the following result. So well, let's see how we can use this uniqueness. So as I said, it doesn't reconstruct q hat, but it tells us it's unique. However, we know from example 1 that this case k of x constant gave a exactly linear spectrum. And so now we know uniqueness, so then exactly linear spectrum implies k of x constant. So that's the case for exactly linear spectrum. This one, you know, if this is exactly linear, it must be a constant k of x. You can ask the question then, okay, is there any other case that's allowed? And in general, I mean, it then depends on what you impose on the system. So in general, you need to solve this inverse spectral problem. However, you can infer more if you assume stronger regularity. So right now, I just looked at the system on the interval from -L over 2 to L over 2. You can unfold, you have normal boundary conditions. You can unfold it to the circle of twice the length. And if you would impose that this system has to be regular, so regular on the unfolded thing, it means that k of x cannot be, it cannot sharply touch the edges of the theory, because then you will have a cusp or something like that, okay? So, but if you were to assume that it has to be regular on the unfolded interval, then there's a stronger thing than Weil's law can be used to show that this is the only case. So it comes from an exact Bohr-Sommerfeld or WKB approach where, well, usual WKB, you would only look at this first term here, and it should be equal to some quantization condition. But you can compute all higher order ones also, and using information from that, and that our spectrum is assumed to be, or has to be integer in the way I mentioned, has to be pi over t times some integer, you can show that the linear case is the only allowed case for having perfect wave transfer in this very regular case, when a system is imposed to be, forced to be very regular. But in general, if you don't impose the regularity, then it's you say it's unclear what's allowed. In principle, there's nothing saying that it's not possible. Okay, so before finishing, let me just give one comment on continuous versus discrete systems. So I highlighted this Wiles law, which gave you an asymptotic condition on the eigenvalues. So that's something that holds for continuous systems. However, for discrete systems, that's not the case because it has an intrinsic UV cutoff, right? You don't have an asymptotic law. And recall, this asymptotic law was what forced the spectrum to behave linearly for large n. Without this condition, you can go as, say, n squared, and many more cases would be possible. So that's kind of going into the details of it to say why it would be possible. In general, it would be more possibilities would be could be allowed. However, you can also look at these bosonic theories that I've presented with a cutoff in place. And if you have a cutoff in place, then you no longer have this condition from Wiles law. Okay. So with that, let's go to the summary. Well, okay, thanks. So what I presented today was an extension of perfect state transfer from discrete systems to continuous systems. Looking now at exploring in detail one particular class of models, those being Tomonaga-Luttinger liquids. But you can so to say the program is to look at other systems as well. So this was like the first exploration of the continuous version of perfect state transfer. And in particular, we studied what are necessary and sufficient conditions. So what you generally will find is that you will obtain an inverse spectral problem, and this inverse spectral problem will answer whether or not you have perfect wave transfer or not. I mean, the ability to solve this inverse spectral problem gives the answer. Okay, and I didn't show it explicitly, but we also extended to homogeneous Tomonaga-Luttinger liquids with a mass term. So then that allows for more possibilities of having perfect wave transfer. And lastly, as I mentioned, we were interested to study other continuous systems, and for many systems, this might not be expected to have perfect wave transfer, but the key thing there is that and that's also been done in the discrete case, that is to look for, well, how close to perfect wave transfer can you come? So that's the concept of almost perfect wave transfer. And another direction is to look at, well, you can allow for effects of curvature and so on based on nonlinear Luttinger liquids. And that's also like one way to approach the problem of looking at more general continuous quantum systems. So with that, I want to thank you for your attention.
But why are you always considering the case of spatial inhomogeneous coupling? I mean, I'm confused by that.
Why they started on the lattice, or why I started it? Both. So on the lattice, you can show that if you're not spatially homogeneous, you have just a constant coupling.
So this result is
will not work
for generic spin chains.
XX.
That's for XX.
XX. So, well, to give some details, you can look at, okay, so XX spin chain. What you can show is that, well, the way they did it originally was in a different way. They looked at a particular case. They looked at specifically these kind of states, okay? But you can do it more generally. So you can also look at the corresponding case when you have more spin-ups, I mean any state. You can show that the Hamiltonian here can be expressed as a Jacobi matrix, so a tridiagonal matrix. With more properties than that, but a Jacobi matrix. And you will find that you have an inverse spectral problem for Jacobi matrices. And now you want to, what I presented now for in the continuum, you you have the same problem for Jacobi matrices. Not Sturm-Liouville operator, Jacobi matrices. The question is then, can you design your couplings such that, well, you're given a spectrum, it also has to be integer, and then you have the questions to find these couplings. And you can show that, well, constant J will not work. This case is 1, but there are other examples. This gives, this will correspond to their corresponding lambda of n going as, actually, En being proportional to n for large n. But there are other examples that are also solutions of this inverse Jacobi problem, inverse eigenvalue problem for Jacobi matrices that has, for instance, this case n squared asymptotically for large n, which is allowed on the lattice because, well, there is no asymptotic condition. There's no Weyer's law. So to answer your question, constant couplings will not work. You have to engineer them in some way. That's one example, but there are many others. And in general, to answer that question, you have to solve this inverse problem for Jacobi matrices. But that's just XX. Of course, you would like to include interactions, but that makes it much harder. And there's a lot of papers written on this case, or this case with I mean, of course, I am assuming nearest neighbor interactions. Nearest neighbor.
You could use GHD.
I'm happy to. So part of the reason I wanted to give the talk is also to perhaps encourage people to look at that. So they look for XX spin chains with nearest neighbor couplings or with next to nearest neighbor couplings, where you get an inverse problem for a pentadiagonal matrix. And then this topic, perfect state transfer on general graphs. But there's at interactions, I don't know of any result. Well, there are some simpler results, but in general, no. You can actually expect that perhaps for XXZ you'll be lucky. I mean, it would be quite a miracle if it would work. But since you're allowed to engineer things in this case, I mean, you take the perspective that I'm allowed to engineer the couplings, I'm allowed to engineer the anisotropy, so on. Then you can ask the question: how close to perfect state transfer can I get?
I don't know if the experimentalists are also allowed to do this.
To some degree, right? You do not have to have perfect control. So actually, that's another key thing that's interesting in this problem. That is, you have to include some uncertainty in there. So how robust are you to having exactly this? So maybe you can realize this on some average or something, but you will not have exactly this profile. So how sensitive are you to perturbations away from this kind of square root behavior? So that's another thing for an experimentalist to tackle. So people have studied this in experiments, and tried to realize it was spin chains, but very short spin chains so far.
So the function is square root of n minus j, or j?
Yeah, n times n minus j. That's the case. Yeah, I wrote perhaps n times. No, sorry.
It's j n.
Yeah. Of course, thanks. Hopefully, anyone watching online later will see this correct. No, j times n minus j. Sorry. Yeah. I mean, what I want to have is this. Yes, of course. Yeah. Otherwise, it's. Sorry. Thanks.
I guess that's why I was asking about the size of the J's, because some of these are probably going to be very large, scaling like system size. So I'm curious as to how that relates to what you were just saying about precision, because if I have these enormous couplings and I just get it 1% wrong,
Yeah,
it's very big.
That's
a very big error.
that's I mean, also why it's quite a challenge to realize this. Or why it's also been realized for very, very short